So let us recapitulate. We have x in Rn, x equals x1, xn, and we have norm x p to be defined as sigma I equals 1 to n mod xi power p whole to the power of 1 over p, where 1 is less than p less than infinity. And we want to show that this satisfies the triangle inequality, so that this will define a norm. We also saw that if this defines a norm, then Rn with this norm is in fact a complete nonlinear space, or in other words, a Banach space. Okay, so we make the following definition. If 1 is less than p less than infinity, the conjugate exponent p star is defined by 1 by p plus 1 by p star equal to 1. So for instance, if p equals 2, then we have that p star is also 2. If p equals 3, then 1 by p is 1 by 3. So you will need 1 by p star is 3 by 2 or 2 by 3, and therefore p star will be 3 by 2, and so on. So this is how we define. So p star, so remark, so 1 will also be less than p star, will also be less than infinity. So now we have a following lemma. AB in R, AB greater than or equal to 0, 1 less than p less than infinity, then a power 1 by p, b power 1 by p star is less than or equal to a by p plus b by p star. So if you look at this, if p equals 2, then p star is also equal to 2, and therefore a power 1 by p, b power 1 by p star is nothing but the square root of ab, and a plus b, the right hand side becomes a plus b by 2, so this is nothing but the arithmetic mean greater than or equal to the geometric mean. So this inequality is a generalization of that particular inequality. So let us try to prove this. Okay, so let t be bigger than or equal to 1 and 0 less than k less than 1. And you look at the function f of t equal to k times t minus 1 minus t power k plus 1. Then what is f dash t? This is nothing but k times 1 minus t to the k minus 1. So t is bigger than or equal to 1, k is less than 1, and therefore this is greater than or equal to 0. So f is an increasing function, and you also have that f of 1 is 0, and therefore f of t is greater than or equal to 0 for all t bigger than or equal to 1. This implies that t power k is less than or equal to k times t minus 1 plus 1. So now, if you look at the inequality which we wanted to prove, you have that if a or b is 0, then there's nothing to prove. This inequality is already okay, and therefore we can assume that a and b are not strictly positive. So in particular, let me assume that a is bigger than or equal to b, strictly bigger than 0. Then I put T equal to A by B and K equals 1 by P. So that, and if I substitute in this, use the fact that 1 by P plus 1 by P star equal to 1, then you would get the inequality which we wanted. If B is bigger than A, then of course we put T equal to B by A and K equals 1 by P star, and then again you will get the inequality. So this inequality is proved. So using this particular lemma, we now prove an important result. So proposition. This is called Helder's inequality. So let 1 less than P less than infinity. P star is the conjugate exponent. Then for xy in Rn, so x equals x1 xn, y equals y1 y1, we have sigma I equals 1 to n mod xi yi is less than or equal to norm xp norm y p star. So this is a very important inequality which we will frequently come across in the future, and therefore we will prove this, take some time to prove this. Okay. So we are going to, again, if x or y is 0, there is nothing to prove in this inequality. So we can assume, so proof, so without loss of generality, we can assume that x is not 0 and y is not 0. Because if one of them is 0, there is nothing to prove. So we now set A equal to mod xi power p by norm xp power p, and b equal to mod yi to the p star by norm y p star to the power of p star. And we apply the previous inequality, a power 1 by p, b power 1 by p star is less than or equal to a by p plus b by p star. This is the inequality which we had. So if you write that, you get mod of xi yi by norm xp norm y p star is less than or equal to 1 by p mod xi power p by norm xp power p and 1 by plus 1 by p star norm yi power p star 1 by norm y p star to the p star. So now you sum over all I, so you get sigma mod xi yi I equals 1 to n by norm xp norm y p star is less than or equal to 1 by p. Now sigma mod xi power p is norm xp power p, so it will cancel. Similarly, 1 by p star times sigma mod yi power p star is nothing but the denominator again, so you get 1 by p plus 1 by p star, which is 1. So now you just cross multiply, you have the result. So this proves the inequality known as Helder's inequality. Okay, so now we can use this to prove the triangle inequality for the norm xp. So we go to the next result. So proposition. So this is called Minkowski's inequality. So we have that if x belongs x and y in Rn, then we have that norm of x plus y p is less than or equal to norm x p plus norm y. Okay, proof. So let us write the power p of the left hand side. So you have norm of x plus y p whole power p is nothing but sigma I equals 1 to n mod xi plus yi power p. And this I am going to break it up as sigma I equals 1 to n mod xi plus yi power p minus 1 into mod xi plus yi, which I am going to write as so less than or equal to, so mod xi plus mod yi. So this is again less than or equal to sigma I equals 1 to n mod xi into mod xi plus yi power p minus 1 plus sigma I equals 1 to n mod yi mod xi plus yi power p minus 1. Now to each of these terms I am going to apply Helder's inequality. So what is the Helder's inequality for this one? So the first one, so let us take sigma I equals 1 to n mod xi plus yi power p minus 1. So this is less than or equal to, so the first one I have to put power p, and so I'll get norm xp, and now I'll get the p star norm of this. So that is in expanded notation. You have mod xi plus yi p minus 1 times p star whole power 1 by p star. Now let us, what is the equation? 1 by p plus 1 by p star equal to 1. So you have p by p star equals p plus p by p star plus 1 equals p. So p minus 1 is nothing but p by p star. So p minus 1 into p star is nothing but p again, and therefore this will be equal to norm xp into sigma I equals 1 to n mod xi plus yi power p whole power 1 by p star. And this is nothing but norm xp norm of x plus y p whole power p by p star. Okay, so you can do the same thing for the second term, and therefore you get norm of x plus y p whole power p is less than or equal to norm xp plus norm yp times norm of x plus y p to the power of p by p star. Now if x plus y is 0, again we have nothing to prove in the Minkowski's inequality. Left hand side is 0, right hand side is non-negative, so it's obviously true. So if x plus y is not 0, then we can divide by this, and therefore you will get norm of x plus y p minus p by p star is less than or equal to norm of xp plus norm of yp. But p minus p by p star is nothing but 1, and therefore you have norm of x plus y p. So p minus p by p star is nothing but 1, because and therefore you get the norm xp plus norm yp. Okay, so this proves the triangle inequality for norm p, and therefore they are all norms. And we also saw that since Cauchy sequence means component-wise Cauchy, coordinate-wise Cauchy, and therefore by the completeness of R, we also get the completeness of Rn for each of these norms. The case of norm infinity is easier than all of this, so I will leave it as an exercise for you to do this. Okay. So this is we have defined a whole family of norms and on finite dimensional spaces on Rn, and you could have done it on Cn as well without any change in any of the proofs, and therefore you have a lot of examples. So now let us come to the question of sequence spaces. So again, we look at 1 less than or equal to p less than infinity, and we define LP to be the set of all sequences xn such that sigma n equals 1 to infinity mod xn power p is finite. So this is a convergent series. So you take sequences xn, so the x1, x2, each vector is now a sequence, and this sequence is given by the property that sigma n equals 1 to infinity mod xn per p is less than infinity, or it's a convergent sequence. As of now, this is just a set, okay? And then we take L infinity is set of all sequences xn which are bounded. So sup over n mod xn is strictly less than infinity. So this is the space. So L infinity is set of all bounded sequences. LP are set of all sequences such that they are p-summable, as you would call it. Okay. So now on LP, so again we will define the norm here. So norm P, norm x P to be equal to sigma mod xn P n equals 1 to infinity whole power 1 by P. And that is finite, and so it's well defined, and you have this. And of course you have norm x in L infinity is equal to sup mod xn over all n. So that is giving you the L infinity norm, which again is well defined because the supremum is finite. Okay, so I will leave it to you to check again that this, just as we did it in the L infinity case in finite dimensions, here also it is obvious that this satisfies all the properties of a norm. So we again have to show here that this is a norm. But before it's a norm, we don't even know that LP is a vector space. So if you take a sequence xn in LP, multiply it by a number alpha, then of course alpha xn, that sequence is also summable. So scalar multiplication is fine. But if you have two sequences xn and yn, what is the guarantee that xn plus yn is also p-summable? So this is a question which we should answer first. Only then LP will become a vector space. Then only it will make sense for us to talk of a non-linear space. We will do both together. So again, all the other properties of norm are obvious. So we will, in one stroke, prove that little lp is a vector space, and simultaneously it will also show that norm xp satisfies the triangle inequality. So let us do that. So let us take x equals xn, y equals yn, xy in LP. So the question is x plus y, which is the sequence got by component wise. So this is the sequence xn plus yn. This belongs to LP. So this is a question which we need to address. Okay, fix k. Then sigma I equals 1 to k mod xi plus yi power p whole power 1 by p. This is the LP norm of x1, x2, xn, xk. By the Minkowski inequality, this is less than or equal to sigma I equals 1 to k mod xi power p whole power 1 by p plus sigma I equals 1 to k mod xi power p mod yi. Whole power 1 by p. Fine. But this left hand side, I can replace it by a bigger sum. So instead of k, I'm going to put infinity there. So this is less than or equal to norm xp, which is defined like this, plus norm yp. So this is true for every k, and therefore I can let k tend to infinity. This side is independent of k, and therefore you get that norm of x plus y p is less than or equal to norm xp plus norm yp, which is finite, of course. And therefore, this shows in one step that x plus y is in LP. So this, we have proved this, and we have also proved simultaneously the triangle inequality. Therefore, all these sequence spaces are non-linear spaces. Okay, so now we want to show so we did this easily. So you can also prove the same trick. So this k trick is a very good trick. So you do it, use the finite result, prove it for all k, and then you pass to the limit, you get the infinite. So as a very simple exercise, you can also try, you can prove the following Helder inequality. So we have x in LP, y in LP star. So we have 1 less than p less than infinity, p star 1 by p plus 1 by p star equal to 1. This is the conjugate exponent. Then you have sigma I equals 1 to infinity mod xi yi is less than or equal to norm xp norm yp star. Again, you, as I said, do this for any k, you will get it up to k, and then you can write this on the left hand side, right hand side, and therefore now you can pass to the limit as k tends to infinity, and so you get this. So you have the Helder set. I forgot to tell you that if p equals 2 equals p star, then Helder is the same as the famous Cauchy-Schwarz inequality, which you might have already come across. Okay. So finally, theorem. LP is a Banach space for every 1 less than or equal to p less than or equal to infinity. So proof. So p equals infinity, I will leave it as an exercise. This again much easier than the previous one. So we want to show that given any Cauchy sequence, so we assume now that 1 is less than or equal to p less than infinity, and so we have to show that every Cauchy sequence is convergent. Okay, so let us take a Cauchy sequence xn. So xn, I will write its coordinates, so it's xn I. Okay, so I is going from 1 to infinity for every fixed n, so the xn equals xn I. So this is a Cauchy sequence. What does it mean? For every epsilon, there exists a capital N such that if nm are greater than or equal to capital N, we have norm xn minus norm xm p is less than epsilon. In other words, sigma I equals 1 to infinity mod xn I minus xm I power p is less than, say, epsilon power p. So this implies for each I we have that xn I is itself Cauchy, and therefore you have that xn I will converge to some xi in R or C. If you are looking at complex sequences, this will be C. Okay. So we have a candidate now for the limit x to be the sequence xi. So here is a candidate. So we want to know if the candidate is eligible. That means you have to answer two questions. So is x in LP, and then norm xn minus x in LP, does it go to 0? If you answer both these questions in the affirmative, that means every Cauchy sequence is convergent, and therefore LP would be a Banach space. Okay, so now let us do this. First of all, it is just as in real line, every Cauchy sequence, so proof, so every Cauchy sequence is bounded. Therefore, there exists a C positive such that norm xn p, is less than or equal to C. This means that sigma I equals 1 to n mod xn I power p is less than or equal to C power p. Therefore, for every k, you have sigma I. So we are going to use the k trick once more. For every k, you have sigma I equals 1 to k mod xn I power p is less than or equal to C power p, because this is smaller than this. But now you can allow n to tend to infinity. You have that sigma I equals 1 to k mod xi power p is less than or equal to C power p, which implies that sigma I equals 1 to infinity mod xi power p is also less than or equal to C power p, because right hand side is independent of k, and therefore you can let k tend to infinity, and this implies that x belongs to LP. Okay, so we have answered the first question, so now we need to answer the second question. So we already saw that for nm greater than n, so epsilon is given, and therefore you have sigma I equals 1 to n infinity mod xn I minus xm I power p is less than epsilon power p. So we do the k trick once more. So this means fix k. So I equals 1 to k mod xn I minus xm I power p is less than epsilon power p. Now you keep n fixed, let n fixed greater than or equal to capital N and m to tend to infinity. So you will get that sigma I equals 1 to k mod xni minus xi power p is less than or equal to epsilon power p. And now this is true for every k, and so this means that norm of xn minus x p is less than or equal to epsilon for all n greater than or equal to n. And that means that xn minus x goes to 0. Therefore, we have shown that the candidate is indeed suitable, and this completes the proof that it is a Banach space. So, okay, so with this we will stop the sequence spaces. So our next example would be function spaces, which we will now look at.